In this section of chapter 15, we'll go over a few homework problems. Now, I just wanted to remind you the definition of equilibrium constant. You write down equilibrium constant like this. When equilibrium is reached, you'd have equilibrium concentrations and then product concentration on the top raised to the power coefficient of balanced reaction, like it's 2 for ammonia, divide by the reactant concentration raised to the power coefficient of balanced reaction. Nitrogen has 1, hydrogen has 3, so that's how we wrote down this equilibrium constant. Now we can define two ways the equilibrium value. One is Kp when it's in atmospheric units, Kc when it's in concentration or molarity units. All these concentrations are expressed in molarity, and then Kp and Kc are related by this expression. Kp equals to Kc times RT delta N raised to the power delta N. But delta N is number of products minus number of reactants. Now, as we go over problems, you'd see how we are going to apply this understanding. Now here we're going to do a problem in which Kc value is given and you're supposed to calculate Kp value. So once you read the question, you know what kind of expression to use. We know one expression that relates Kp and Kc. Let's write down that expression so that you know that Kp equals to Kc RT raised to the power delta N. Now let's write down the chemical reaction first for 21, and they're all in gas phase. So PCl3 plus Cl2 giving PCl5. This is already a balanced reaction, so I don't need to worry about balancing. What I need to write down is what information is given and what is missing. Now let's see what information is given. We have Kc value 0.042. It looks like they didn't give you any unit, even this inverse of molarity unit, because we have one product and two reactants. Temperature equals to 500 Kelvin. If this were given in degree centigrade, we'd be adding 273 to change it to Kelvin. R value is known, which is the gas constant, 0.0821 liter atmosphere Kelvin mole. So this gives you all the information that we need to do this problem. Since we are going to use this expression where delta N is needed, so let's calculate delta N. Delta N will be given by products minus reactants. I have one product, which is PCl5, and two reactants. PCl3 is one of them, Cl2 is the other one, so that's -1. So now we are going to apply this following expression. Kp equals to Kcrt delta N. So Kp would be given by Kc value we already know, 0.042. Now 0.042 is the Kc value, Rt is 0.0821. Obviously it's the liter atmosphere per degree Kelvin per mole, and temperature is 500 Kelvin. 500 Kelvin, and we need to, let's use this bracket and here a parenthesis, and this should be raised to the power -1 because delta N is -1. So what I get is 1.023 times 10 to the -3. Now, if they had all these units given to you, 0.042 would have been inverse of molarity. And the final unit for Kp would be inverse of atmosphere. So I don't know why they left out the units. So anyway, this is the answer to this question. Now we're going to do number 23C. In number 23C, again, there is an equilibrium reaction is given. And in C, they're asking for Kc value of a reverse reaction. Not only just reverse reaction, let me write down the reaction so that you can see this, how they're related. So 2NO, so let me write down the reaction. NO plus Br2, that gives 2NOBr. Again, these are all gas phases, and Kc value is given for this reaction, so the Kc is 1.3 times 10 to the negative 2, 1.3 times 10 to the negative 2, that's given at 1000 Kelvin. So the question is, of course, this Kc goes with this reaction. So the question is, what is the Kc value, and let's call it Kc prime. What is that value for a differently balanced reaction? Not only the differently balanced, it's also reverse reaction. NOBr on the left hand side giving NO plus half Br2. So first let's write down expression for Kc and Kc prime. That way you can see how they're related. Okay, let me first write down Kc, NOBr on the top, raised to the power 2 because that's the coefficient of the balanced reaction, NO on the bottom, raised to the power 2. These are all equilibrium concentrations, and Br2 raised to the power 1 because there is 1 Br. So let me double check whether I copied everything right. Now this is for Kc expression, this is the reaction, and I double checked. Now let's write down expression for Kc prime for the second reaction. So Kc prime will be given by concentration of NO raised to the power 1, concentration of Br2 raised to the power 1/2, and concentration of NOBr raised to the power 1. Okay, now how do I find a relationship between them? Because this is what we need to find out, this value. Well, it looks like if I take the inverse of the Kc, then I can put this NO and Br2 on the top. And let's do that so that I can think better. 1 of Kc equals to NO, square is now on the top, Br2 raised to the power 1 is on the top, NOBr raised to the power 2 is on the top. Now at least I have NO and Br2 on the top and NOBr on the bottom so that I can compare. Now how are they related? Kc prime looks like that 1 over Kc is square of Kc prime. And indeed, if you square this, let me show you with the different color of the ink. If you square this whole thing, you get equal to this. So let me write it down like this: Kc prime squared. Hopefully you understand that. And we already know the Kc value, and obviously we can just plug in inverse of Kc value. Kc value is this, 1.3 times 10 to the negative 2. So 1 over 1.3 times 10 to the negative 2 is inverse of Kc, equals to Kc prime squared. Since we're looking for Kc prime, which would be square root of 1 over 1.3 times 10 to the negative 2. And that value I found out to be 8.77. I can round it off to 8.8. So that's the answer to our question, because they're asking for Kc of this second reaction. Let us now discuss problem number 37, page 644. Now, if you look at the reaction and you see that it's a balanced reaction, the 2 moles of NO, when it is used up, it uses up 2 moles of hydrogen, and 1 mole of nitrogen is formed and 2 moles of H2O is formed. So this is how we understand a reaction happens. So it pretty much based on a stoichiometric ratio, that's 2 to 1, 2. That's how the reaction happens. Now for this reaction, initial concentration of NO is given, which is 0.100. For hydrogen is 0.050, and for H2O is 0.100 moles per liter, because they gave you the volume of 1 liter. In addition to that, they also gave a final or equilibrium concentration for NO. That means initial concentration was 0.100, and the final concentration after reaching equilibrium was obviously less, 0.062. So what happened to the difference? The difference was used up. So from 0.100 to 0.062, we find out how much was used up in the reaction. So we find that 0.038 molar was used up. Once I know the moles of NO used up, I can quickly find out moles of hydrogen used up, because from a stoichiometric ratio it's this 2 and 2, it's the same number. So when you got NO used up is 0.038, I can right away write down hydrogen used up would be 0.038 from the above reaction. On the other hand, nitrogen formed would be 1/2 of the value of hydrogen used up or NO used up. So that's why we took 1/2 of 0.038. That gives you 0.019. Moles of H2O formed, that's same as moles of hydrogen used up or moles of NO used up. Again, we're looking at all these coefficients, 2, 2, and 2. So now we can write down that H2O formed is 0.038, same as that of hydrogen or NO. So make sure you understand that. Now once we know how much of hydrogen was used up or how much of nitrogen is formed, we can always calculate equilibrium concentrations. For example, from hydrogen, initial concentration was 0.050. Out of that, 0.038 was used up. So keep in mind, 0.038 was used up by the time it reached equilibrium. So the equilibrium concentration would be given by subtraction of these numbers. Initial value minus the final value. Initial value minus how much was used up. So that's the final value or equilibrium value. In case of nitrogen, at the beginning there was no nitrogen. Otherwise they would have told you that. So there was 0 at the beginning, but there was some extra nitrogen formed, was 0.019. That's what we have shown you here, how much nitrogen was formed. So you add them up, you get 0.019 molar equilibrium concentration for nitrogen. Similarly, for H2O formed, 0.038 molar additional amount of H2O was formed. At the beginning, there was 0.100 molar H2O. So final concentration would be sum of these two numbers. So 0.138 molar concentration of H2O at equilibrium. Since we have all these equilibrium values, we just plug in all these numbers into H2O, NO, and H2, and that's how you get this expression. Make sure you double check the power, because sometimes we make mistake in copying these numbers. So 0.019 raised to the power 1, that's for nitrogen, and 0.138 raised to the power 2, that's for H2O. So let's double check that. Yeah, that's for H2O. And then you have, at the bottom, you have NO. And NO value, we know that's 0.062. We already calculated that number, 0.062. That's this value already given at equilibrium. And then we have value for H2, equilibrium value for H2, which is 0.012. And again, the powers are same as coefficients of balanced reaction, so we double check that, and this gives 6.5 times 10 to the power 2 per molarity. Now we're going to discuss number 51. Now this is page number 645. They're saying that at 2000 degrees centigrade, the equilibrium constant for the reaction 2NO, let's first write down the reaction, 2NO plus, actually there's 2NO giving N2 plus O2. So this is the reaction for which Kc is given. Kc equals to 2.4 times 10 cubed. That's the given value of Kc. Initial concentration of NO is given, so let's use different initial concentration. I'll put down IN 0.175. Now question is, what is the equilibrium concentration or final concentration after equilibrium is reached for NO, N2, and O2? Okay, so we read the question and wrote down the given information and what we're supposed to calculate. Now, in this particular case, since initial concentration is given for NO, let's set up an expression like this. Initial, INIT, 0.175. When you just started the experiment, there was no nitrogen or oxygen. Now, otherwise they would have told you how much nitrogen was there when you allowed NO to react. In order to reach equilibrium, a part of NO has to react. So it's going to form some products, and finally forward reaction rate would be equal to reverse reaction rate. Now let's assume that X is the quantity that was used up. So NO, already we have 0.175. Out of that, X has been used up by the time it reached equilibrium. Now, chemical reaction, as I mentioned before, deals with how much is used up and how much is being formed. So here we have 2. Let's write down those coefficients. 2 on the top, 1 on the top of nitrogen, 1 on the top of oxygen. So what it tells us that when 2 moles of NO is used up, 1 mole of nitrogen would form and 1 mole of oxygen will form. Okay, now if that is the case, when I said that X of NO is used up, N2 formed would be half of that number because you see it's 1. So x over 2, I hope you all understand that, and this would also be x over 2. Remember, we are going by these coefficients and how they're related. 2, 1, 1, so 1 is half of 2. So that's why amount of nitrogen formed would be x over 2, because x is the quantity of NO that was used up. So now I can write down Kc expression. So Kc would be given by concentration of NO. Let's write down that, not to confuse you. Nitrogen at equilibrium, oxygen at equilibrium, and NO at equilibrium raised to the power 2 because there's a coefficient 2. Now just plug in those x values, and I'm going to write down, let's change the color of the pen, x over 2 times x over 2 in place of nitrogen and oxygen. At the bottom you have NO value, which is 0.175 minus x squared. So I just plugged in the expressions for N2, O2, and NO. Let's double check all these numbers. So hopefully we haven't made any mistake here. Now that equals to Kc, and Kc value is already given. We know this 2.4 times 10 to the power 3. So Kc is 2.4 times 10 cubed. And that's equals to, now I can see that x over 2 by x over 2 is x squared by 4. So what we need to do is write down here in a simplified version. Let's draw a line here so that we can x squared by 2 squared, and then you would have 0.175 at the bottom. You have minus x squared. Now let's take a square root of that. So on the left hand side we get 48.99. 48.99 equals to x over 2 times 0.175 minus x. So square is gone now because we took a square root of both sides of this expression. And then you can multiply both sides by 2 to give 98.98, and then do the multiplication of 0.175 minus x on both sides, and then you finally get x value. I would like you to do in detail so that you double check my calculation. So what I get is the following: 17.15 on the top, make sure you double check that, divided by 98.98, and that gives me 0.173. Now x over 2, which is the concentration due to nitrogen and oxygen, so that's value of nitrogen equals to oxygen equals to 0.087. That's what I got after rounding off, 0.087. So that's the value for nitrogen and hydrogen. And about NO, we know the initial value, which is 0.175. 0.175 minus x, minus 0.173. Remember, we got this x value, minus 0.173, minus 0.173. Sorry, we are running out of space here. It's going to give me 0.002 molar. So these are the answers to these questions, and hopefully you understood this. Let me now discuss problem number 54. This is a heterogeneous equilibrium given, so let me write down that first, that NH4SH NH4 SH, and that's the solid. So let's write down solid now at the bottom. Usually I write down the state of the matter when it's heterogeneous so that I know which one is solid and which one is gas. Ammonia is a gas plus H2S, that's also gas. So you can clearly see that. Let's write down this more clearly. The solid ammonium NH4SH is the solid, and other two are gases. Now what is given here? Kc value 1.2 times 10 to the negative 4. Now they're asking for equilibrium concentrations for ammonia and H2S. So ammonia equilibrium and H2S equilibrium. So that's what we need to find out based on the given information. Now, in order to write down any equilibrium expression, let's assume that the initial concentration of NH4HS is A. At that time, there was no product formation, so it's 0 and 0. At equilibrium, part of the reactant would use up. Let's call it X. So X being used up, the leftover is going to be A minus X. Now we know here that in this reaction it's a 1-1-1 reaction. This is one of this, one of ammonia, one of H2S. You can always find out whether it's balanced or not, and it is balanced. 3, 4, 5 hydrogen, 5 hydrogen, 1 sulfur, 1 nitrogen. It's a good idea to double check. When X of NH4SH breaks down, you get X of ammonia, X of H2S. Let me explain it again. If one NH4SH breaks down, you get 1 ammonia, 1 H2S. If 2 NH4SH breaks down, you get 2 NH3 and 2 H2S, because we ought to maintain those stoichiometric ratio. If X breaks down, then you get X of ammonia, X of H2S. Okay, now I can write down Kc expression, or equilibrium constant expression, is given by ammonia equilibrium concentration raised to the power 1, H2S equilibrium concentration raised to the power 1, NH4 SH concentration raised to the power 1. Only thing is the bottom one is solid, so ignore it or assume it to be 1, because that concentration doesn't change, and we explained that before. So now I'm going to plug in the X's instead of ammonia and H2S. So X times X will be on the top and just 1 is on the bottom. So this is equals to X squared. Now we know the Kc value, which is given. So 1.2 times 10 to the negative 4 equals to X squared. So from here we find out that X equals to, taking square root of both sides, you get X equals to 0.0109, and I can round off to 0.011. And that's the concentration of NH3 and H2S. So let me write down our final answer. NH3 at equilibrium concentration equals to concentration of H2S, and that value is 0.011 molar. So this is the answer. So ammonia concentration is 0.011. H2S concentration is also 0.011. So when both concentrations are the same.